these are going to be the materials we're going to be using for this project. It's going to be a breadboard, a power supply module, some jumper cables, a 9-volt battery, 2 transistors, 2 2K ohm resistors, one 330 ohm resistor, 2 push buttons, and an LED. These are going to be our circuit diagrams for the 4 logic gates that we're going to be wiring today, as well as their logic truth tables. This is the buffer logic gate, the NOT logic gate, the AND logic gate, and the OR logic gate. This is the circuit diagram for the buffer logic gate. Our logic truth table says that if we have an input of a 0, we're going to have an output of a 0. If we have an input of a 1, we're going to have an output of a 1. Our first case, it's when we have an input of a 0, meaning that this switch is going to be off. The current is going to flow into this resistor, but it's going to get stuck here. It's going to go into this other resistor, into the LED, and into the collector of the transistor. There's not going to be any current going into the base of the transistor, meaning that the electrons that are supposed to be coming from the emitter of the transistor into the LED and into this whole circuit, it's going to be disconnected, meaning that the LED is going to be off. Our second case, it's when our input is 1, meaning that the switch is going to be turned on, meaning that current is now going to flow into the resistor, into the switch, and into the base of the transistor. It's going to go into this resistor, into the LED, and into the collector branch of the transistor. Now the electrons can move from the emitter of the transistor into this whole circuit, meaning that the LED is going to be turning on. This is a circuit diagram for the NOT logic gate. Our logic truth table says that if we have an input of a 0, we're going to have an output of a 1. If we have an input of a 1, we're going to have an output of a 0. Our first case is when we have an input of a 0, meaning that the current is going to flow into the resistor, but it's not going to flow into the switch since it's not turned on. It's going to flow into the other branch. It's going to go into the resistor, but since the LED and the transistor are in parallel, it's just going to go into the LED. There's going to be electrons coming in from the other side, meaning that it's going to connect here in parallel, meaning that the LED is going to be turning on. For our second case, we're going to have an input of a 1, meaning that this switch is going to be turning on. There's going to be current flowing into this resistor, into this switch, and into the base of the transistor. There's going to be current flowing on this branch, going to go into this resistor. Since the LED and the transistor are in parallel, it's going to move into the collector branch of the transistor. Since there's going to be current flowing from the base of the transistor, there's going to be electrons moving from this other side. They're going to go into the emitter of the transistor since this whole thing is connected, meaning that the LED is not going to be turning on. Our third circuit diagram is going to be for our AND logic gate. Our logic truth table says that we now have 2 inputs, which are A and B, and 1 output, which is C. If we have 2 inputs of a 0, we're going to have an output of a 0. If we have B as an input of a 1, we're going to have an output of a 0. If we have only A as an input of a 1, we're going to have C as an input of a 0. If we have both inputs A and B as 1s, we're going to have C as 1, meaning that the LED is going to turn on. For our first case, we're going to have 2 inputs of a 0s, meaning that there's going to be current flowing through both resistors, but not through the switches since they're not connected. It's going to flow in through here. It's going to go into the resistor, into the LED, but it's just going to get stuck here since there's nothing coming in into the bases of the transistors, meaning that no electrons are going to be coming in from the other side into the emitters of both transistors, meaning that the LED is going to be off. Our second case, it's when we only have B as 1, meaning that B, it's going to be the switch is going to be turned on, meaning that there's going to be current flowing in through here. It's going to get stuck here. There's going to be current flowing in through the resistor and into the switch. It's going to go into the base of this transistor. There's going to be current flowing into the other side right here. Going to go into the resistor. It's going to go into the LED. And it's going to connect through here. But there's nothing going to be happening into the other transistor since there's not going to be any electrons coming into the emitters, meaning that the LED is going to be turning off. Our third case is when we have an input of a 1 at switch A, which is going to be this switch. There's going to be current flowing into this resistor, into this switch, and into the base of this transistor. There's going to be current flowing into the resistor, but it's going to get stuck at this switch. It's going to go into this other branch, into the resistor, and into the LED. There's going to be electrons coming into this side, but since there's no current going into this base of this transistor, this whole branch, it's going to be disconnected, meaning that the LED is not going to be turning on. Our final case, it's when both inputs are 1, meaning that both switches are going to be turned on, meaning that current is going to flow into the resistors and into the switches, meaning that current is going to flow into the bases of the transistors. There's going to be current also flowing into this resistor, into the LED. It's going to all be connecting to the transistors. There's going to be electrons coming in from the other side into the emitters of the transistors, meaning that the LED is going to be turning on. The last circuit diagram is going to be for our OR logic gate. Our logic truth table says that we have 2 inputs, A and B, and 1 output, which is C. If we have both inputs at 0, we're going to have an output of a 0. If we have only B as an input of a 1, we're going to have an output of a 1. If we have only A as an input of a 1, we're going to have an output of a 1. And if we have 2 inputs as 1, we're going to have an output of a 1. Our first case is when we have both inputs at 0, meaning that both switches are not going to be turned on. There's going to be a problem because the current is going to flow through these both resistors. There's going to get stuck at the switches. There's going to be current flowing into this resistor, into the LED. Since the transistors are in parallel, there's nothing going on here in the current, meaning that no electrons are going to be coming onto the emitters of both transistors, meaning that the LED is going to be turning off. Our second case, it's when we have an input of a 1 at B, meaning that only this switch is going to be turning on. This means that the current is going to flow into this resistor. It's going to get stuck here, meaning that the base of this transistor is not going to get any current, meaning that this whole thing is not going to work. There's going to be current going into this resistor, into this switch since it's turned on, and it's going to go into the base of this transistor. There's going to be current going on this branch. It's going to go into this resistor and into the LED. Since both of these transistors are in parallel, there's nothing going to happen on this transistor, meaning that the current is going to go into the collector branch of this transistor. There's already current going into the base. There's going to be electrons coming from the other side, going to go into the left into this emitter of this transistor, meaning that the LED is going to be turning on. Our third case, it's when only A has an input of 1, meaning that now this switch is going to be turning on. Current is going to flow into this resistor, into this switch, and into the base of this transistor. It's not going to flow into this resistor. It's just going to get stuck here. Current is going to flow into this resistor, into this LED. Since both transistors are in parallel, it's going to go into the collector of this transistor. Since this switch is going to be turned off, there's going to be no electrons coming in from this side going into this transistor through the emitter. Since there's not going to be any current going into the base of this transistor, current is going to go into the collector of this transistor, and electrons are going to be moving into the emitter. Current is going to flow through this switch into the base of the transistor, meaning that this thing's going to be connecting, meaning that the LED is going to be turning on. And finally, we have our last case. It is when both A and B have inputs of a 1, meaning that both of these switches are going to be turning on. This means that current is going to flow through both resistors, through both switches, and into the bases of each transistor. The current is going to go into this branch, into this resistor, into the LED, but it doesn't really matter since the transistors are in parallel. The current is going to go into both collector branches of the transistors. There's going to be electrons coming on from the other side. They're still going to go into the emitter of both transistors. Since there's current coming in from the bases, this whole thing is going to be connected, meaning that the LED is going to be turning on. Now we're going to test our first logic gate, the buffer logic gate. Our truth table says that there's only one input, which is A, and one output, which is C. Our first case, it's when both A and C are 0, meaning that if I don't press anything, the LED should be off, which it is. And our second case, it's when both A and C are 1, meaning that if I press A, the LED should be turning on, which it is. Now we're going to test our NOT logic gate. Our truth table says that there's only one input, which is A, and one output, which is C. Our first case, it's when A is 0 and C is equal to 1, meaning that if I'm not pressing anything, the LED should be turning on, which it is. And our second case is when A is 1, meaning that C is equal to 0. As you could see, I'm pressing A and our LED is off, which it is. Our third logic gate is our AND logic gate. Our truth table says that we have two inputs, A and B, and one output, which is C. Our first case, it's when both A and B are 0, meaning that C is 0. I'm not pressing anything, so right now the LED should be off. Our second case, it's when only B is 1, A is 0, meaning that C is 0. So as you could see, I'm pressing B here, the LED is off. Our third case is when we only have A as 1, B as 0, and C is 0. So I'm going to press A, the LED is off. And our last case, it's when both A and B are 1, meaning that C is going to be 1. So as you could see, I'm pressing both A and B and our LED should be turning on, which it is. And finally, we're going to test our OR logic gate. Our truth table says that we have two inputs, which are A and B, and our output is going to be C, which is either the light turning on or turning off. Our first case is when both A and B are 0. Our C should be 0, meaning that the LED is off. And as you can see, I'm not pressing anything, so the LED is off. Our second case is when only B is 1, A is 0, and C is 1. So if I only press B, the LED should be turning on, which it is. Our third case is when only A is 1, B is 0, and C is 1, meaning that if I only press A, the LED should be turning on, which it is. And our final case is when both A and B are 1, our C should be 1, meaning that if I press both, the LED should be turning on, which it is.